Hello, my students. I welcome you all to today's lesson. And today we are going to be treating the topic refraction of light waves. The specific objectives for this lesson includes: number one, explain how the direction of light changes as it travels from one medium to another. Number two, deduce a value of refractive index of a given material from measurements of angles of incidence and refraction. Number three, explain the meaning of critical angle and total internal reflection, stating the conditions under which they occur. And finally, number four, establish the relationship between the critical angle and refractive index and apply it to the solution of simple problems. Let's define refraction. Refraction could simply be defined as the bending of a light ray as it crosses the boundary between two media of different density, thus causing a change in its direction. We can also define refraction as the change in the speed and direction of a light ray as it crosses the boundary between two media of different densities. This phenomenon of refraction is responsible for the following observation: the bottom of a clear river or pond appears shallower than it really is. A rod or spoon appears bent or broken when it is partially immersed in water. Then we'll have that letters in print seems to be nearer when we place a thick glass block over them. These are the things that we observe in everyday's life. When you go to a pond or swimming pool, you will notice that something that is at the bottom appears to be closer to the surface of the water. Or you might be looking at the pool and you think that the depth is just maybe 10 meters. But by the time you enter, you find out that it's up to 15 meters. Okay? Now, let's look at the refraction through rectangular glass block. Normally in the laboratory, we can demonstrate refraction of light using a rectangular glass block. We can also use a triangular glass block, but today we'll be looking at rectangular glass block. If you look at the diagram you have there, you will see a rectangular glass block labeled A, B, C, D. And you can see a ray of light, PO. Please follow the instruction, the guide as I'm explaining them. PO, that's the incident ray, as you can see there. And we have a refracted ray, OR. As the ray passes from air to the glass block, it's what bends. You can see that it changes direction. So that is the definition of refraction: the change or the bending in the speed or direction of a wave as it crosses the boundary between two media of different densities. Now you can see the ray later came out, and you have another ray there, RS, and that ray, you can see that is parallel to the first ray, which is the incident ray. Okay, now we have an angle between this incident ray PO and N there. The N is normal. What is normal? Normal is a perpendicular line drawn to a plane surface. So you can see that that surface is plane, AB is plane. So that line drawn there, which we have N tagged to it, is our normal, a perpendicular line drawn to a plane surface. So the angle between this incident ray and the normal is called the angle of incidence. We also have another angle there, which is the angle between the refracted ray OR and the normal, and that angle is called the angle of refraction. We also, after the ray comes out from the glass, there is another angle there labeled small letter E. And what is small letter E? It is the angle between the emergent ray, you can see your emergent ray there, and also the normal. We have another normal for that surface DC, plane surface DC. So the angle between that normal drawn there and the emergent ray is called the angle of emergence. Okay, we do this in the laboratory using optical pins to verify refraction through rectangular glass block. During our practical class, we are going to explain further. Okay, now let's look at the laws of refraction. In exam, if you are asked to state the laws of refraction, you have to give us the two of them at once. Don't give one and leave the other one. They must go together. And these laws, we have number one, that the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. And the second one, the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media. The ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media. And this second part of this law is called, or also called, the Snell's law. Mathematically, we have an expression for that. N is equals to sine I all over sine R, where N is a constant known as the refractive index of the second medium. Also, we have that the refractive index is also given by V1 all over V2, where V1 is the velocity in the first medium and V2 is the velocity in the second medium. Remember, we said that there is what? A change in speed or velocity as this ray travels from one medium to another. Okay, now if we go further, we have that from what we have studied, we know that our V is equals to F lambda. Our velocity is given by F multiplied by wavelength. The lambda there is wavelength. If we substitute this into the first equation, that is the previous equation, V1 over V2, will now be having that our N is equals to F lambda 1 all over F lambda 2. And F will cancel out there, and we'll have that refractive index is also given by lambda 1 all over lambda 2, where lambda 1 is the wavelength in the first medium, lambda 2 is the wavelength in the second medium. And we are asked to take a proper note about frequency during refraction. The only quantity that remains constant during refraction is frequency. So we don't have F1 or F2. So that's why we now have the final equation there that our N is equals to lambda 1 all over lambda 2. Let's take a site example. We have a ray of light is incident on a body X as shown in the diagram below. What is the refractive index of the body? And we have a diagram there, which is our rectangular glass block. The ray travels from A to that medium X. Okay, it has the shape of that our triangular prism, rectangular glass block. Okay, if we look at that question and we solve it effectively, we will be having that our idea, if we look well, we should be able to take note that our angle of incidence is not that 30 there, but 60. Why is it 60? Remember, we have defined angle of incidence as the angle between the normal and the incident ray. So the one given is the angle between the incident ray and the plane surface, and that is not your angle of incidence. So we have 90 minus 30 will give us the angle of incidence. The other side of the inside the body X, we also have a value there which is 50, but that 50 is the angle between the refracted ray and the plane surface. So we will not use it as our R, angle of refraction. So what do? We will have 90 minus 50, which will now give us 40. So we are going to use 60 for our angle of incidence and 40 for our angle of refraction, because angle of refraction is the angle between the refracted ray and the normal. Please take note of that. It's just a little distraction just to know whether you actually know what you're supposed to do. Okay, let's look at the solution to that question. Finally, we have that our refractive index, the formula is sine I all over sine R, and substituting we have sine 60 all over sine 40, and that will give us 0.8660 all over 0.6428, and we have our refractive index to be 1.35. Okay, we take a second example there. Surface waves traveling in deep water at 15 meters per second are incident at a shallow water boundary. If the angles of incidence and refraction are 45 degrees and 30 degrees respectively, calculate the speed of waves in shallow water. If you look at the solution to that question, we already know our refractive index formula, sine I all over sine R, which can also be equal to V1 all over V2. So if we make use of that equation, we will now have that our V2 cross multiplying will now be equal to V1 sine R all over sine I. Substituting, we have 15 sine 30 degrees all over sine 45 degrees. And that will make our V2 to be equals to 7.5 over 0.7071. And the final answer to that question is 10.6 meters per second. All right, we take a site heading, and that site heading is real and apparent depth. Real and apparent depth. Just like the first introduction to some of the phenomenon that refraction is responsible for. When you look above the surface of a pool or a river, it appears shallower than it's supposed to be. Okay, or when you have a print written on a paper and you put a glass block on this on that ink, you notice that the ink appears to be closer to the surface of the glass block. All these are due to what? Apparent depth. Okay, now we have that the real depth, the apparent depth, and the refractive index are related by the formula n is equals to real depth all over apparent depth. Okay, so if we want to get our real depth or apparent depth or refractive index, we can use that relation between the three of them. Let's look at a simple example there. If the real depth of a river is 10 meters, but its apparent depth is 7.5 meters, then the refractive index of the river is given by refractive index of the river water is given by, we have our formula already, so we have that our n is equal to real depth all over apparent depth, and the real depth is 10, apparent depth is 7.5. If we do that, we will have our final answer, which is n is equal to 1.33. Note, refractive index has no unit. Okay, let's take a second example. What is the real depth of a swimming pool which appears to be 10 meters deep when viewed directly from above its surface? In bracket, we have the refractive index of water to be 4/3. Using our formula again to get the solution to that question, we have that our n is equals to real depth all over apparent depth. So we have 4/3 for our refractive index is equal to, we are looking for the real depth all over apparent depth is 10. If we cross multiply, we will now have that the value of our real depth is 4 times 10. 4 times 10 all over 3. I'm sorry about that. That should be 3, not 2. Okay? 4 times 10 all over 3. But the answer is correct. The final answer there is 13.13 meters. Okay? We now take a side heading. Total internal reflection. Total internal reflection. What is total internal reflection? This is a phenomenon that occurs when light travels from an optically more dense medium to an optically less dense medium, and the angle of incidence in the denser medium is greater than the critical angle. That's the definition of total internal reflection, or one can say that it occurs when light travels from an optically dense medium to an optically less dense medium, and the angle of incidence in the denser medium is greater than the critical angle. To understand total internal reflection well, we have to define critical angle. What is critical angle? Critical angle is the angle of incidence in the denser medium when the angle of refraction in the less dense medium is 90 degrees. It is the angle of incidence in the denser medium when the angle of refraction in the less dense medium is 90 degrees. We can explain the two using the diagram below. If you look at that diagram is, we call that semicircular prism. We use a semicircular glass block to demonstrate total internal reflection. Let's explain. We have the first diagram there. You can see there is an incident ray there, which is OA. Look well, you see OA there. Okay. Now what happened? Normally when light travels from a denser medium, when we say denser, density, let's picture it as something that is heavier, and when we say less dense, lighter, okay? But that is for a layman to understand, but we use the word less dense or denser. So when light travels from a denser medium to a less dense medium, the refracted ray moves away from the normal. The refracted ray moves away from the normal. Or on the contrary, if the light is traveling from a less dense medium to a denser medium, the refracted ray bends towards the normal. So in this case of total internal reflection, the ray is incident on a denser medium, that is glass. Glass is denser than air. So the ray is incident on the glass, and what happens here, you can see that once the ray crosses the boundary between the glass semicircular prism and the air, what happened? The refracted ray now bends away from the normal. Okay, and we also have a weak reflected ray, very weak reflected ray there. Okay, the second diagram again, what is happening there? If we increase the angle of incidence, the refracted ray will keep on bending away from the normal. Please take note of that. From what I have said before, that when light travels from a denser to a less dense medium, that the refracted ray moves away from the normal. So if you keep on increasing the angle of incidence, the refracted ray will keep on moving away from the normal. And a certain point will be reached when this refracted ray will lie parallel to the plane surface, as you can see in the second diagram. Okay, so in the second diagram, we have increased the angle of incidence OA, and what happened? The refracted ray now continue to move away from the normal to the point that is now lying parallel to the plane surface. And you can see we have a strong refracted ray there. Strong refracted ray, but there is also a weak reflected ray inside the prism. But now, our main concern there is that critical angle. Definition there, that it is the angle of incidence in the denser medium when the angle of refraction in the less dense medium is 90 degrees. You can see that what you have in the second diagram is critical angle, because now we have increased the incident ray such a way that the refracted ray now is lying parallel to the plane surface. So the angle between the refracted ray and the normal is 90 degrees. So you have critical angle at that moment. The angle of incidence in the denser medium, when the angle of refraction in the less dense medium is 90 degrees. Now the third one, that is the third diagram there, will now show us what the total internal reflection. If we increase this ray or the angle of incidence again, what will happen? There wouldn't be any refraction. We will have total internal reflection. So you can see that we have strong reflected ray and no refraction. Yes, because if you increase it, it will keep on moving away from the normal, and at this point it will now move into the what? The prism or the glass, and at that point you have total internal reflection. And that is why we have defined total internal reflection based on what? That light is traveling from a what? Optically more dense medium to an optically less dense medium, as you can see in the diagram, and the angle of incidence is now greater than the critical angle. So that angle of incidence in the third diagram there is greater than the critical angle that we had in B part of the diagram. So that explains that very well. So the next thing we are going to look at now is very simple, which is conditions for total internal reflection to occur. Conditions for total internal reflection to occur. We have already discussed that. And number one is that light must travel from an optically more dense medium to an optically less dense medium. And number two, that the angle of incidence in the denser medium must be greater than the critical angle. Very simple. That is what we use in defining or explaining total internal reflection. And that explanation also gives us the conditions for total internal reflection to take place. Okay, now we have a relationship between the critical angle and refractive index, and that relationship is that our refractive index is equals to 1 all over sine c. N is equals to 1 all over sine c, where c there is our critical angle. So we can now solve simply with that example there. The refractive index of a medium relative to air is 1.8. Calculate to the nearest degree the critical angle for the medium. That is simple. Solution, we have our formula there. N is equal to 1 all over sine c, and if we make sine c the subject formula, because we are looking for critical angle, we now have that sine c is equal to 1 all over 1.8, which will now give us 0.5556. Then we make c our critical angle the subject formula, and we have that our c is equals to the sine inverse of 0.5556, and that will give us 33.75, and to the nearest degree we now have 34 degrees. Okay, the next thing we are going to look at now is applications of total internal reflection. Applications of total internal reflection. Number one, in nature, total internal reflection could be seen in a mirage. We're used to mirage. Normally when you are driving on an express way or express road, when the sun is out in the afternoon on a sunny day, at a certain distance you start to see on the road as if there is pool of water, but as you drive closer to the water, the water disappears. What is causing that? Total internal reflection. Also, we have in nature again, we have B, field of view of a fish underwater. A fish underwater will be able to see, or is able to see, what objects on the surface of the water through total internal reflection. Number two, the phenomenon of total internal reflection is used in many optical instruments like telescopes, microscopes, binoculars, spectroscopes, and periscopes. These are the instruments that apply the principle of total internal reflection in their what? Operations. Number 3, the brilliance of diamond is also due to total internal reflection. And finally, number 4, optical fibers. Optical fibers work on the principle of total internal reflection. We use optical fibers in communication, and they operate on the principle of what? Total internal reflection. Okay, I think we have exhausted what we have for that topic, refraction of light waves, and I'm going to leave us with just little assignment here. You can see that on your screen. Number 1, a transparent rectangular block 5.0 cm thick is placed on a black dot. The dot, when viewed from above, is seen 3.0 cm from the top of the block. Calculate the refractive index of the material of the block. Number 2, the refractive index of a material is 1.5. Calculate the critical angle at the glass air interface. And finally, number 3, radio waves travel in air at 3 times 10 raised to power 8 meters per second. If the waves enter water of refractive index 3/4, calculate the speed of radio waves in water. That's where we will draw the curtain for today till we meet in our next lesson. Have a nice day.